Okay, so today we will go through an overview of how Linux, the memory management mechanism of Linux. So how Linux, the OS, tries to manage the memory, meaning RAM, how it juggles with various objects to which one to put into RAM and how. So it's an overview. So not going too much in depth. Uh, so this is the doc from Red Hat. Um, so how does the memory allocation happens in Linux? So uh, here's the here's the picture uh, that the doc gave. So we have this RAM, and so RAM can allocate a lot of address. It has a lot of address, and those addresses can hold memory. So you if you uh, indicate that, okay, from this address to that address a block of memory should reside, then a RAM does that. But the problem of using RAM without any other layer if the program tries to straightforward use the RAM instead of going through any other mechanism, then the problem happens is that memory get defragmented within the RAM. Meaning, let's say an object, the program is trying to store an object into the RAM. Okay, so it stores the RAM inside the RAM from address 1 to 3. Then another program may come up and it wants to allocate RAM as well. So it can let's say allocates from 4 to 8. But the first program then again wants to allocate further a lot more memory. Then it has to go from 9 to later, right? So the RAM itself will get defragmented. The data will inside the RAM will get defragmented. There will be a lot of spaces will go waste because there will be holes inside the RAM that are not getting used. So to combat all those issues, what Linux does is that it uses virtual addressing. So in this picture, as we're seeing, we've got this physical address. These addresses are the real address of the RAM, okay? And we've got this virtual address, and CPU sits between the physical and the virtual address. So what CPU does is that it converts this physical address to this virtual address and exposes the virtual address to the kernel and the rest of the programs. So what eventually happens is that programs and services and all those processes, what they do is that when they want to allocate the RAM, so they request to the kernel, and kernel gives them the virtual addresses, and those virtual addresses are treated like the real address by those processors. So they do not really distinguish between the I'm talking about the processes. So from the perspective of those processors, it's as though they're dealing with the real RAM. But what actually happening is that the kernel exposed the virtual RAM to those processes, and the virtual RAM is being treated by the processes like a real RAM. So the advantage of this mechanism is that the address management becomes much more easier. The kernel, it can easily defragment or reorganize the memory. Paging becomes easier, and the virtual addresses are directly mapped with the physical addresses, which are the real address of the RAM. Okay, so we've got this virtual address. These are not exposed to the program. The program actually, or the processes are actually speaking with the virtual addresses, and processor itself is sitting between these two, the physical and virtual address, and it is translating. So there are a lot of issues that come up when this kind of translation occurs. Let's say a page can become invalidated because, let's say, the process is trying to the CPU is trying to address a memory that does not really the address does not really it is not a real address. So then it has to remap or reorganize. Okay, so the mapping has to refresh. Okay, so there has to happen some refresh mechanism between the virtual and the physical address to keep both of them up to date. Okay, so the address translation mechanism happens, as well as the translation look aside buffer. So there is this TLB, translation look aside buffer. The two main components in this translation mechanism are page tables and translation look aside buffers. Page tables are multi-level tables in physical memory that contains mapping of the virtual memory. So this is what page tables are, and the mapping are readable by the virtual memory translation hardware in the processor. So processor does all those things. So also the cache of this our processors, the modern processors, they do have level 1, level 2, level 3 caches. So those caches, they come in handy in terms of doing all those tasks. Okay, so so that's the main gist of it, and the doc goes a little bit deeper. We won't go into so much in depth of this topic, because we're trying to actually just get an overview and save a lot of time, because knowing too much doesn't always help. We just have to really just understand what is actually going on with the OS. Okay, and so let's get into some programs that Linux gave us by default. So one of which is free, so we just become okay. I've given wrong password. Okay, so we have this free program, and we have vmstat. So these two programs we have. So free, it gives us a lot of information about the state of the RAM. We also have htop. We can use htop to get an overview of the of everything from processes to CPU usage to RAM usage, all this. We have vmstat. What vmstat does is it shows us information about the virtual memory. So as we have seen the virtual addresses, so it deals with the virtual memory. So first let's open up htop. So htop, so it's the PC that I'm currently using. It has two memory sticks, so two RAMs installed in it. One 8 gig DDR4 RAM, another one is 16 gig DDR4 RAM. So in total we have like 23 gigs of RAM installed. So this is the total, as you are seeing. So that is the total amount of memory. So 22.9 gig of memory, and it is showing that okay, we have like 4.9 or 5 gig of memory that is being used, and the rest of the RAM is free. So 5 gig in use and 22 gig or 23 gig memory we have in total in our hand. So 5 gig out of 23 gig, so it is less than 1/4 of memory. But if we see the bars, that the indicator bars, then we're seeing that okay, more than 15%, 50% is filled up. So like we have this green portion and then blue and then yellow. So what are these? Okay, so it is showing okay, I have more than 50% of the memory is allocated, but it is also saying that okay, I have like 5 gigs of memory being used and the rest of them is probably free. Okay, so the blue here, the blue and the yellow, what these two indicate is that it indicates the buffer memory and the cache that is allocated inside that memory. So these two are taking a huge amount of space. So further, if let's see, let me just open it pen over here. So I'm using this Tilex terminal, so in case if you are wondering. So here let's run the free command. Okay, so free m. Okay, let's free m. So this is in megabyte or free help, and I need to show it in so it is in maybe byte. Okay, so maybe byte meaning that okay, it is considering this that okay, 2 to the power n, it is showing me in binary it is converting from binary to decimal. It is not megabyte, it is maybe byte, so 1024 bits. So let's keep it running. Okay, and also we have this buffer and cache showing us together. So let's separate them out with the W option. So zoom it a little bit and keep them in on watch. So watch -n. So for each 1 second, free -m -w. This is keeping it is running every 1 second. So according to this, we have total 23 gigs of memory. Fine, and the used memory is like, how about in SI unit? Let's also show in SI unit. How about that? Help. Where is the help menu? In human readable format, which is SI. How about that? Okay, sorry. So not human readable meaning SIM. So that is also wrong. Sorry guys, so I'm taking a little bit of time. So how about M? Okay, maybe not that straightforward. M doesn't really help. B. So M. Okay, so how about free M SI? Okay, so this is working fine. You know what? Binary was better. Okay, let's keep this running. So we have 23 gigs of memory in total, because I have one 8 gig RAM with 16 gig another 16 gig RAM, so the total is like 24 gig, out of which 23 gigs is available, and then used is like 6 gigs of RAM is being used, and then out of that we have like 11 gigs of RAM free. Shared is 326, buffer is 16 100 at a megabyte of data in buffer. We have like around 6 gigs of cache, and then available is 17,000 gigs. 17 gigs. Okay, so 17,000 megabit maybe bytes or 17,000 gigs. So, and also we have another program called vmstat. So let's run that as well. So watch in every 1 second vmstat w wide okay. So I need to be root, so let's become root. Watch minus in 1 vmstat minus w minus m, not minus m but rather vmstat. Let me just check help. So I want to show the unit, so the unit is s, unit is s m. So the free do not match. How about capital M? Yeah, so yeah, this is another output. Okay, so here we've got this vmstat output, and we've got this free m output. These two are pretty similar, because if you check the cache in both of those outputs, the cache size are same, or the buffer is same. So what is exactly showing in these two? So let's check the free comment. So free dash m is showing us the free memory, the shared buffer, cache, and available. So what is the available amount of memory? So 17 gigs of memory it is showing as available, but we have total like 23 gigs of total memory, out of which already 6 gigs of memory is being used, but it is still showing that I have 17 gig available. Why? Well, because it is the available, this column shows the estimation of how much memory the Linux kernel will be able to free if a new program or a process wants to allocate some memory to the system, to the RAM. Okay, so it means that 17 gigs of memory is possible to allocate by freeing up all the buffer, all the caches, all the including the free memory. Okay, so free is like 10 gigs of free memory. I've got 6 gigs in use, so total 16, and then here we have 6 and like 2, so that is 8 gigs of memory. So 16 plus 8, that is 24. So I'm rounding up, so the total amount of memory, it sums up to be the same, but the available does not mean that this amount of memory is right now free and not being used. The available column means that the Linux operating system can free up this much amount of memory if a new process wants to allocate this much amount of memory. So how will it free this 17 gig? By maybe managing the buffer and cache, by deleting this buffer and cache, and also using this free memory, and also maybe, okay, so this is, and also the swap is 0 because we are not using any swap space. Swap is when your memory, maybe your memory is not sufficient, so but you need more space, so a portion of your disk is used as a swap space to put the contents of your memory into the disk temporarily. But this system that we're currently using do not have any swap space configured, so the swap size is showing here 0. Okay, So now the question is, what's the difference between buffer and cache? So we've got this buffer, shared, and cache. So what's the difference between buffer and cache? So buffer is basically a type of memory. So it's like a zone, or it's a memory. So let's say that various processes that are trying to communicate among each other. So how are they sending data among themselves? Okay, so maybe you have got one process trying to communicate with another process. It needs to send some data to this process. How is it doing? It is doing through this buffer memory, buffer portion of the whole memory. So this is what the total amount of buffer. So processes are using this to transmit data among themselves, and also kernel uses this buffer area to reorganize the incoming data. So all the data that are coming from various processes, various I/O operations, these this data is not organized, and the buffer is used to reorganize all those data. So what is cache then? Okay, so cache is basically it's a database. It is like a database that is inside the memory. So all those processes, they are working with some data, right? So no matter which software you use, it works with some data. So where those data reside? So these data are inside this cache. So quickly so nothing goes to the CPU directly from hard drive. Okay, so it has to be put or loaded inside the RAM, and from that RAM, CPU works with the data of that RAM. Okay, and the cache is a temporary storage of those data. So this is what cache is basically. Okay, so and to understand these outputs from vmstat, we have got this great article over here from Red Hat as well. So this is an article on vmstat. So how does vmstat so this is the output of vmstat. Okay, so R here, let me just put this over here, and this one over here. Okay, let me just reduce the size a little bit better, maybe. Okay, so here, make it larger, a bit larger. Okay, it will do. So here we've got this proc portion, then memory, then swap, then IO, then system, then CPU. Okay, so here R is the number of processes waiting for runtime. B is the number of processes in uninterruptible sleep. Swapped. So this is for swap the amount of virtual memory used, and free is the free. So this matches with this one. So the free memory that is unused, totally unused, nothing is inside this free. So we've got also buffer and cache, and then swap. Both of them are 0 because we don't have swap space configured. IO is the block input and block output. Okay. So BI means blocks received from block devices. BO means blocks sent to the block. So this is basically the input output to the disk. So if you want to say that, okay, I have a lot of IO going on, okay, whether I have an IO issue or a CPU waiting issue or a RAM allocation issue, so you check this vmstat command and you look for, okay, whether I have a lot of read request or lot of disk write request or not. And then these two are from for system. System in means the number of interrupts per second, including the clock. CS means the number of context switches per second. So context switching is happening, and these are all time. So US means the time spent running non-kernel code. SY, time spent running kernel code. ID, time spent idle. WA, time spent waiting for IO. ST, time stolen from a virtual machine prior to Linux. So something unknown. Okay, you know what? And it also shows a lot of good examples. So let me just pull that back again. So here it also gave a lot of example, like, so the user ran this command. So what this command do is that it reads random data, and it basically writes random data to the disk. So what this is really doing is that it just increase the SY count to 93, 96, 97, 93%. Well, why? Because generating random number is an expensive process by the CPU, so this is why the SY column got high. Okay, and yeah, so and the time execution. So and this next example is RAM bottleneck or swapping example. Here many applications will be open, including VirtualBox, and so a lot of application like a VirtualBox virtual machine requires a lot of memory to run. Okay, it's because these are expensive, memory expensive. Windows guest system, like, then more application like Open Office, all those things just overwhelm the RAM usage. So a lot of swap is getting used. So the RAM is filled up, and we've got a lot of cache buffer, so swapping memory pages to the swap file. So swap out, so this got high, swap out got high because a lot of swapping is taking place. Okay, so this is an example of high read. So it also uses this dd command. It is reading a lot of reading an ISO file, big ISO file. What it is essentially doing is that it is increasing the IO operation, meaning the BI block input is just tremendously high because it is just reading a large ISO file. Okay, high IO write output. So this dd command, it is it's not really reading anything because it is pointing to dev 0, but it is writing like 500 meg of file with block size 1 meg. It is just writing to the file, and this is why it is like a lot of block output is generating. And here a lot of CPU wait is happening. What's happening over here? So in this following an update DB process is already running. The update DB utility is part of mlocate. So this is for searching. So basically update DB is examining the entire file system, accordingly creates the database, internal database for locate command, meaning it's an alternative to find. Because update DB reads all of the file names of the entire file system, the CPU must wait to get data from the IO system. For that reason, vmstat running in parallel will display a large value of WA. So the waiting got high, the waiting time. So these four are time basically. So the this one got high because a lot of it is just checking out a lot of files, so all those files it is going through due to the update TV. Okay, so this is what basically the vmstat command in general means. And also I'll say that another use of vmstat is vmstat, again let me go to help, and vmstat imp. Okay, so this one, so again let me run it through watch. One vmstat imp and su yeah. Okay, so so this is another usage of vmstat. So what's this im? It is showing the memory slabs. So what are memory slabs basically? So we've got these pages, right? So memory itself is arranged by pages. So we have a lot of page inside the we use these memory pages, and to organize all of those pages these slabs are used. So each program, it can have a lot of slabs. So these are for XFS, these are for the cache, DM, fuse, all those IPv6. So each slab means it's like a database of memory. Okay, so from address 1 to address something, it's got a lot of memory, and the memory is filled with objects. So the num column means that it is the number of, I guess, the number of objects. Again, let's get back to the, where's the, so let's see this slab info. Slab, where is it? Okay, so here it is. So the cache name is the name of the slab cache. This often indicates what type of objects are stored in that cache. Okay, so let's put it on the right side. So here we have got this KVM vCPU. Let me just cross it out for now. Okay, and then we've got this num, the total number of objects, both used and unused, that are currently inside that cache. So in this cache we've got 0 objects right now. In, let's say, in this cache XFS buff we have got 7,326 objects, and the total is the total number of objects that can be inside that inside that cache before it grows further. Okay, so it is the maximum number of total size, but it can grow. Okay, so if the number of objects grow, then the total size will also grow. The size, it is the size of the object in byte, and this is the pages. So the number of pages with at least 1 active objects. So this is what it shows. So this is the slab information. And also another thing that you can use to vmstat is f. So this is showing the number of forks. So what are forks? Forks are basically, you know, if a process spawns another process, it creates another process without killing itself, then it is a fork. Let's say a parent process, it generates like 5 other processes, but the parent process still is alive, then it is a forking. Okay, so how many forks are happening? This is showing here. So yeah, so this is the use of vmstat, more or less. And also we've got this vmstat s, so watch minus n1 vmstat s. So what is it basically is showing is the, so it is pretty much self-explanatory, meaning the number of total memory, used memory, active, inactive, then how much is in buffer, how much is free, how much is for swap, all those information. And if you want to get into deeper analysis, you can pick data from here. So this is pretty much how it's an overview of Linux memory management system. So again, just to overview, so this is the main thing. We've got this physical memory and this virtual memory, and CPU is doing all those translation, and you can check out your buffer usage. So one of the realizations that I have got from all of this is that, even though your memory usage is showing like 5 gig or whatever it is not actually the case, as we're seeing that more than 50% of the memory is already allocated because of the buffer and the cache. So how much memory is really good for your system? So clearly, so we've got like 22 gigs, so more than 11 gig or 12 gig is currently is being used, accumulating both the buffer and the cache and the used and the shared memory, putting all together, it will go well beyond 12 gig. So I would say that more modern systems should at least have 16 gigs of memory installed in them. 8 gigs do not cut these days because using Chrome is really expensive. As we're seeing here, a lot of memory is for OBS, and then we've got a lot of CPU usage for Chrome, because Chrome it takes a lot of memory, 2 to 3 gigs easily it consumes, Chrome alone. So yeah, so just don't consider only the used or the used memory and this much. Okay, so the total memory used is 6 gigs, so this is the amount of memory I need, so 8 GB is fine. This is absolutely not the case because buffer and cache, these are very, very important. Why? Well, the more cache you have, the less IO operation you will get on your SSD or your hard disk. This will not only increase the longevity of your SSD, but also make your CPU usage, your CPU will be well used. What happens nowadays is that these 9 gen, 10 gen, 11 and 12 up to 14 gen CPUs, these CPUs are pretty strong, pretty powerful. So if you are not pairing a good quality of RAM with those CPUs, then you are not taking the full advantage of those new generation CPUs. Okay, so not only if you provide a lot of RAM to the CPU, it not only makes the system much more efficient, but it reduces IO, it increases the longevity of your CPU as well as your hard drive or your SSD, whatever you have. So yeah, more RAM is always a good thing. Okay, so yeah, so that's for today. That is the overall thing we got out of learning all these things, studying all those things. Okay, so please follow my channel, and please do comment how I can improve the video quality, and the way I explain how can I make myself better for you guys. And also please suggest me on which topic do you want to see me doing video, or try me trying to explain you in the next video. So if you have any topic suggestion, so please do put your suggestion in the comment section, and please do consider subscribing. Bye bye.